Method to determine order of reaction. Three methods to determine the order of reaction, which are initial rate method, linear graph method, and half-life method. Initial rate method. First, use the concentration measurement to find the initial rate. Use initial rates from several experiments to find reaction orders, and then use these values to calculate rate constant. For example, determine the rate law and calculate the rate constant for the following reaction from the following data. F2 reacts with 2ClO2 to produce 2FClO2. We have 3 experiments here for this chemical reaction. Means this reaction is done 3 times, so 3 experiments. For experiment 1, the concentration of F2 is 0.1, concentration ClO2 0.01, and the initial rate 1.2 times 10 power of negative 3. So this is the rate of reaction, molar per second. This is the rate of reaction for experiment 1. And for experiment 2, the concentration of F2 is 0.1, concentration ClO2 0.04, and this is the initial rate. And so on for experiment 3. First, in order to find the order of reaction using initial rate method, we select any two experiments which the reactant concentration of both experiments are the same. For example, here we have experiment 1 and experiment 2, which reactant F2 reactant, both values are the same. So you can select experiment 1 and experiment 2 because these two values or concentration are the same. Or you can also select experiment 1 and experiment 3 because the concentration of reactant ClO2 is 0.01, and for experiment 3 also 0.01. That's the first step. Select any two experiments which reactant concentration of both experiments are the same. So I want to select experiment 1 and experiment 3. So this one, experiment 1 and 3, because the concentration of ClO2 for experiment 1 and experiment 3 are the same. And then write down the rate law. We have this chemical equation here. You can write down the rate law. Note that in the rate law there is no product, only the reactant. So rate equal to K F2, this is a reactant, and to the power of X. This power is the order of reaction. We don't know the order of reaction, so that's why X, and then ClO2 Y, the order of reaction for ClO2. So this is the rate law for this chemical equation. Then second one, write the rate law. This is the rate law. And then find order in F2 using ClO2 constant, means the same value of ClO2. You can find out the order of F2. Reaction order of F2 can be determined when you have the same concentration of ClO2 by dividing the rate. So you have experiment 3, so usually the larger value divide the smaller value. So this initial rate 2.4 times 10 power of negative 3, this initial rate 1.2. So that's why rate experiment 3 divide rate experiment 1. So if you divide the rate here, 2.4 divide 1.2, and then this is the rate. Note that use the rate law. So rate divide, so if this is rate 3, and then on the top one you have to put the rate law for experiment 3. Okay, so this is rate 3, so on the top part, rate law for experiment 3. So K concentration F2. The concentration F2 experiment 3 is 0.2, so that's why I substitute here 0.2, and then we don't know the order, so X, and the concentration ClO2 for experiment 3, 0.01, so substitute here, and then over rate 1 means over the rate law for experiment 1. So Kf2, concentration for experiment 1, 0.1, and then ClO2, 0.01 for experiment 1, and then cross out or cancel out the same value on top and below. So cancel out K, because K over K is 1, and then 0.01 power of Y divided by 0.001 power of Y is equal to 1, so cancel out, leaving you with 2.4 times 10 power of negative 3 over 1.2 times 10 power of negative 3 equal 0.2 to the power of x over 0.1 to the power of x, leaving you with these values only. And then when you have this value, you will get 2 to the power of 1 when 2.4 times 10 power of negative 3 divide 1.2 times 10 power of negative 3, you will get 2. 2 is equal to 2 to the power of 1, that is 2. 2 to the power of 1 equal to 0.2 divided by 0.1, here 0.2 divided by 0.1 power x. So 0.2 divided by 0.1 is equal to 2 power of x. So 2 power 1 equal to power x. So we know that this x is equal to 1. When x is equal to 1 means the power is 1. So this is x is the power for f here. When you look at the rate law, x is the power for f2. So you can say that it is first order with respect to f2. Okay, this is the first order. F2 has the first order reaction. And then we want to find out the value of y. If we want to find out the value of y, you need to find the constant value for f2, same value for f2, which is 0.1, 0.1. So you have to select these two experiments, experiment 1 and experiment 2, because we need to find out y. And then repeat again, select any two experiments. So we already have the power for f2. So now we need to find the power of ClO2, which is y value. So in order to find the y value, you have to cancel out the f2. If you want to cancel out the f2, select two experiments which f2 have the same concentration, which is experiment 2 and experiment 1. And then usually the larger value of rate of reaction will divide by the smaller value. So experiment rate 2 divide experiment 1. So rate 2 over rate 1 equal, so whatever rate law for experiment 2, substitute. So here 4.8 times 10 to the power of negative 3 equal K 0.1x 0.04y, and then here the rate law for experiment 1, 1.2 times 10 to the power of negative 3 K 0.1 to the power of x 0.01 to the power of y. So cancel out the value on top and below, which are the same, and then you will get 4.8 times 10 to the power of negative 3 over 1.2 times 10 to the power of negative 3 equals 0.04 power of y over 0.01 power of y. So if you divide 4.8 divided by 1.2, you'll get 4, and 4 is equal to 4 to the power of 1, and this one you'll get 4. So 4 to the power of 1 equal 4 to the power of y. We know that y is equal to 1. So this is first order with respect to ClO2 as well. So F2 first order, ClO2 is also first order. So you can write the rate law, determine rate law. So you can write the rate law rate equal KF2 to the power 1 ClO2 to the power 1. You don't have to write to the power 1 because it's understood as this is the first order of reaction. So in order to find the rate constant, the K value, we already have the rate law here, both to the power 1, both first order. This is the rate law. And in order to find the value of K here, you can select any experiment that you want. Choose one experiment only. So let's say we choose experiment 1. Substitute all the values of experiment 1 into this rate law equation and you will get the K value. For example, we use experiment 1. So rate for experiment 1 is 1.2 times 10 power of negative 3 equal K, and then concentration F2 0.1 times concentration ClO2 0.01, and solve this equation and you will get the K value equal 1.2 per molar per second. The K unit must be in second order. Why? K unit must be in the overall order reaction. Why second order? Because power 1 for F2, power 1 for ClO2. So 1 plus 1 is equal to 2. So the overall order for this rate of reaction is second order. Overall order is second order. So the unit of K must be the overall order unit. So this is second order. So that's why per molar per second. Linear graph method. Construct a table which consists of time, concentration of reactant, ln reactant, and 1 over concentration of reactant. This is for the zero order, first order, and second order. Plot reactant concentration versus time for zero order, ln concentration of reactant versus time for first order, and 1 over concentration of reactant versus time for second order. The linear graph confirms the order of reaction. Means after you plot these three graphs, the graph which is linear, that is the order of reaction. That is linear graph method. For example, for this one, you plot three graphs. This is for the zero order graph, first order graph, and second order graph. The first order graph shows the linear graph, so the reaction is first order in N2O5. That's how you determine the order of reaction using linear graph method. For zero order, linear graph, slope equal negative K. For first order, slope is equal to negative K as well. But for second order, slope equal to K. Because its gradient is positive, these two, 0, and first order gradient is negative. Next, half-life method. You have to plot the concentration of reactant versus time, determine the first half-life and second half-life from the graph. From there, you can determine the order of reaction and the rate constant from the graph. From the following data, determine the order of reaction, half-life, and rate constant, given time and the concentration of the reactant. So you have to plot the concentration of reactant on the y-axis and the time on the x-axis. Plot the graph and look at the half-life. So if you look at here, the first half-life, first here you have 1. The concentration of C2H5 is 1 molar, and then half of 1 is 0.5. So if you look at 0.5, half of the initial concentration means half-life. 0.5, the time taken for the concentration to become 0.5 molar is 70 minutes. And then the second half-life is half of the 0.5. Half of 0.5 is 0.25. So check 0.25, the time taken for the concentration to become 0.25 molar is 1 It's 140. So the first half-life 70 minutes, second half-life is 140. So the first half-life 70 minutes, the second half-life it's also 70 minutes. The time taken is also 70 minutes. 70 to becomes 140, it's also 70 minutes. So from here you can conclude that first half-life is equal to the second half-life. If first half-life is equal to the second half-life, it is the first order of reaction. From the following data, determine order of reaction, half-life, and the rate constant. We have already determined the order of reaction, which is first order, and then the half-life already get 70 minutes from the graph, and rate constant K. In order to find K, we can use the half-life equation. Half-life T half equal ln 2 over K. We already have half-life 70 minutes. For the initial concentration to become halves, it's 70 minutes. Substitute 70 for T half, and then ln 2 with value 0.693 divide by 70 minutes, and you get the K value 9.9 times 10 to the power of negative 3 per minute. This is the unit for K for the first order reaction.